This is going to be the lecture over section 27.3. We're going to look at the relativity of time. So if delta T naught is the time interval between two events that occur at the same space point in a particular reference frame, is called proper time. If the first frame moves with a constant velocity u relative to a second frame, the time interval between the events as observed in the second frame is going to be longer than that. How much longer? Well, this much longer. This effect is called time dilation. So a clock moving with respect to an observer appears to run more slowly than a clock that is at rest in the observer's reference frame. So to Julianne, the light pulse arrives and reflects along a straight line. To Justin, the light pulse travels at the same speed but follows a longer path with the interval. Okay. So if a train passes through a certain station at 12 and then another at 12:05, the station master sees a time interval of 5 minutes between the trains. How would the conductor on the front of the train measure this time interval, and what result would he get? So to answer these questions, let's consider another thought experiment. As before, frame of reference, S prime, perhaps the moving train, moves along the common x-axis with a constant speed u relative to a frame S, say the station platform. For reasons that will become clear, we assume that u is always less than the speed of light. A passenger, Julianne, at O prime, moving with frame S prime, detects or directs a flash of light at a mirror a distance b away. She measures the time interval for light to make the round trip to the mirror and back. And we use the subscript 0 as a reminder that the timing apparatus is at rest in reference frame S prime. So the total distance is going to be 2d because it comes to the source, gets there, and bounces back. We use the subscript 0. Oh, wait, I just went through that. And the light flash moves with constant speed c. So the time interval delta T naught is the distance 2d that the light flashes divided by the speed. In other words, this c here is going to be the distance traveled divided by the time, like you normally get velocity. And we're going to call S prime Julianne's rest frame because she's not moving. She's just sitting there on the train. The time for the round trip is measured by Justin, who is standing there, luggage in hand, off the train. Well, luggage is not in hand. Is in a different time interval. He's in frame S, and the time interval is delta T. We don't know what it is, so we're going to try to figure that out. During this trip, the light source moves at constant speed, u, in relation to S. In time, it moves a distance of u times delta T, in other words, velocity times time. The total round trip distance as seen by S is not just 2d, but 2l. In other words, the light source is moving and the light is traveling in this direction and then bounces off the mirror and comes back in this direction. So what he is observing is the light going from here to here, and that's a longer distance than what's going here. So how do you figure out what that distance L happens to be? Well, using a little bit of knowledge here as to how far that travels and the height here or whatnot, you can figure out here that L is going to be the square root of the distance squared plus this distance divided by 2 squared. You can look at it as a triangle. If you cut it here, you got a right triangle. So you take the distance d here and you take half of this distance and take the square root of it using the Pythagorean theorem. That's what you got. So if you go through and you want to figure out what the delta t happens to be, you take 2l divided by c. You know what L is now. So you slap that in and place a bell. And you want to have a relationship here that doesn't contain the distance d. Since that's part of the S prime reference frame, you'd like to have everything related to this. So how do you get rid of d? Well, to get rid of d, well, I should say here that you would like to have everything in this reference frame, but you're also trying to figure out what T naught happens to be in this relationship. So I shouldn't say that so much. What I can say is you'd like to replace D with something that would allow you to get to the value T naught. And so if you replace D with this, you put this in here and you can successfully square both sides, rearrange the terms, and eventually you come out with this relationship. So if two events occur at the same point in space in a particular frame of reference, and if the time interval between them is measured by an observer at rest in this frame, is delta T naught, and then an observer in a second frame. In other words, we're going, this is the one where we measure delta T naught, and so now we're looking at this guy who is at a different reference frame, the second one. Then observer in a second reference frame using moving with constant velocity u relative to the first frame measures a longer time interval. And that's what we mean by the time dilation. And the time interval is measured by this. So again, u is going to be the velocity of S prime which is moving relative to S. This is the time interval between two events at the same point in reference frame S prime. And the denominator is always less than unity, so delta T is always going to be greater than delta T naught. One way to look at that is that moving clocks run slow. So, I mean, if you thought of an old-fashioned pendulum clock that ticks once a second, as observed by its reference frame, this is T naught. When the time between ticks is measured by an observer in the frame that's moving with velocity u, then the time interval this, he observes is longer than 1 second. And so he thinks that clock is running slow. Clock moving with respect to an observer appears to run more slowly than a clock that is at rest in the observer's reference frame. So this is a conclusion is a direct result of the fact that the speed of light is the same in both frames of reference. Two special cases are worth noting. First, if the velocity u of reference frame S prime relative to S is much less than c, then this is much less than 1. In that case, the denominator is nearly equal to 1, and that the equation reduces to the Newtonian relationship. In other words, you got to be moving close to the speed of light for this to matter. And that's why you don't see relativistic effects in everyday life. And second, if u is greater than c, then the denominator is the square root of a negative number and is thus an imaginary number. This suggests that speeds greater than c are impossible, at least according to the theories that we have now. So proper time. There is only one frame of reference in which the clock is at rest, but there are infinitely many in which it is moving. So therefore, the time interval measured between two events that occur at the same point is a more fundamental quantity than the interval between the events that occur at different points. So we're going to use the term proper time to describe the time interval between two events that occur at the same point. So the time interval delta t isn't a proper time interval because it is the interval between two events that occur at different spatial points in the frame of reference S. Therefore, it can't really be measured by a single observer at rest, but we can use two observers, one stationary at the location and the other at the second, each with his or her own clock. So we can synchronize these two clocks without difficulty, as long as they are at rest in the same frame of reference. So in other words, we can send a light pulse simultaneously to the two clocks from a point midway between them. When the pulse arrives, the observers set their clocks to the prearranged time, but note that clocks synchronized in one frame of reference are generally not synchronized in the other frame. So in thought experiments, it's often helpful to imagine many observers with synchronized clocks at rest at various points in a particular frame of reference. So we can picture a frame of reference as a conditional grid with lots of synchronized clocks distributed around it, like this. You got a grid here is three-dimensional. There are identical planes of clocks that are parallel to the page in front, back, behind, connected by grid lines parallel to the page. Only when a clock is moving relative to a given frame of reference do we have to watch for ambiguities of synchronization or simultaneity. So you've got several problems and tutorials that I would encourage you to go through. Um, you've got space travel and a twin paradox. Time dilation has some interesting consequences. So suppose you want to explore a planet in a distant solar system 200 light years away. Could a person possibly live long enough to survive the trip? 1 light year is the distance light travels in 1 year. In ordinary units, turns out to be this distance. Even if the spaceship can attain a speed of 0.999 times the speed of light, in other words, 99.9% of the speed of light, relative to Earth, the trip requires nearly 200 years, as observed in Earth's initial reference frame. But the aging of the astronauts is determined by the time measured in the spaceship's frame. So with reference to this equation, the change in time is time interval measured on Earth, and delta T naught is the corresponding proper time interval measured in the moving spaceship. Spaceship speed relative to Earth is this. Then what you're finding out here is that observers on Earth think the trip lasts for 200 years, but to the astronauts on the spaceship, the time interval is only about 9 years. But there's another problem. So suppose the astronauts want to come back home to Earth. The time dilation equation suggests an apparent paradox called the twin paradox. So let's say you've got two identical astronauts named Eartha and Astrid. Eartha remains on Earth while Astrid takes off and that high-speed trip. And because of time dilation, Eartha sees all of Astrid's life processes, such as her heartbeat, proceeding more slowly than her own. Thus, Eartha thinks that Astrid ages more slowly. So when Astrid returns to Earth, she should be younger than Eartha. The paradox comes about because all inertial frames are equivalent. Kant Astrid made exactly the same arguments to conclude that Eartha is in fact the twin. Then each thinks that the other is younger, and that's the paradox. So to resolve that, we recognize that the twins are not identical in all respects. Eartha remains an inertial reference frame at all times. Astrid must have an acceleration with respect to inertial reference frames during the part of the trip in order to turn around and come back. Eartha remains always at rest in the same inertial reference frame. Astrid does not. Therefore, there is a real physical difference between the circumstances, and careful analysis shows that Eartha is correct. When Astrid returns, she is younger